I'm pleased to be here to talk to you. I'm going to try to make this informal to be to accord with the surroundings. And I'm here for a conference in ubiquitous computing. I don't know the background of folks, though. The proof, what's it called? The school that? Proof Society. Is that theoretical proofs? So so I did work. My graduate degree at the Programming Research Group at Oxford was in formal methods applied to software engineering problems. So I was a pseudo theoretician. Others that are here are faculty, students, research with the Computational Foundry. Okay, so I want to try to encourage you at the beginning at least to speculate with me about how to solve particular problems for the future using different ways of thinking about computing. Before I get too much into detail, I want to let you know that my thoughts have been influenced by people from very different disciplinary approaches. This is just 4 I'm showing here, 3 of whom fall in the area of chemical engineering, material science, and then one in the bottom left-hand corner is Thad Starner, who's a colleague of mine at Georgia Tech, who actually was the lead for the development of Google Glass maybe 5-6 years ago. So he's a leader in wearable technology. Okay, so I'm not going to assume this audience knows too much about the area of ubiquitous computing, right? Raise your hand if this is the first time you've heard the expression ubiquitous computing. Yeah, great. Okay, so I'm going to tell, this is a vision of kinds of applications of computing technology that's about 30 years old. Not the first to have that particular vision, but I'm going to revisit that particular vision that's influenced a lot of certain class of computer scientists over the last 30 years, myself included. And I'm going to just have us reflect on whether we've gotten to where that vision suggested or not, and if not, how we might get there. And then I'm going to show you some examples of work I've done over the last 3 years with my colleagues at Georgia Tech in a topic that I call computational materials. And I'll explain what those are and give 2, 3, 4 examples of those that we've developed to try to get you thinking about what I mean by this new approach to way you might build a computer or a computational device. And then if we have time, we'll talk a little bit about some research opportunities that span all of computing. And I'll conclude with what I hope the main purpose of this talk is to get people who think about the use of computing devices to think in different ways about what a computer is and what it might do. So, in 1991, in Scientific American, Mark Weiser, who at the time was a senior scientist at Xerox PARC, familiar with Xerox PARC, that brought us the personal computer revolution, or at least one of the big players, Ethernet. And that was in the late 60s, early 70s. In the late 80s, that's when Mark Weiser was leading a lab that he called the Ubiquitous Computing Project. And after a few years and some demonstrations of these examples, he wrote this very influential article in Scientific American called The Computer for the 21st Century. And the very first line was, "The most profound technologies are those that disappear." But what he meant wasn't necessarily that they would shrink away in terms of their physical size. That was part of it, but that wasn't what he really meant. He meant that they would become so pervasive, so common in our everyday lives that we would stop thinking about computers as computers. And he used a couple of analogies like the electric motor, which when introduced, the idea was that each home would have one big motor and there would be a series of rods and whatever that would distribute the electricity or the electrical movement throughout a home. And we know that's not the way we think about electric motors now. They're everywhere, and the only time typically we know about an electric motor is when it stops working. He also chose another technology, language, as a technology that we don't think about, but it's everywhere in our everyday lives, and we rely on it, but it has kind of disappeared from our consciousness in terms of printed word, the spoken word, things like that. So that's what he was thinking, that computing by the late 80s was poised to make this leap to become this invisible technology. And the second line of that article said, "They weave themselves into the fabric of everyday life until they are indistinguishable from it." And he meant that metaphorically. But if we look today in 2019, we can actually revisit this vision and say, well, have we gotten there? Our computers essentially vanished from our consciousness, but because they are everywhere. And if so, have they woven themselves into the fabric of everyday life? And we could try to interpret that a little more literally. So I want to take you through a couple exercises here to give you an aspirational goal that I have about comparing computers to other kinds of everyday objects. So you're familiar with these objects here, the Post-it note that you probably all have either in your bags or in your desks available to use whatever. And you can use it for many different things. It could be a temporary bookmark. You can write various notes, place the things. You can use them. You can make little paper airplanes and shoot them across a room. You can do lots of things with them. But one of the things you can't do with a Post-it note is something that's computational. So what if I could take a Post-it note, I leave my office, and I write a little note, says, if you have a message to leave for me, just tap that red button and speak the message to Gregory. And what if after you tap that and you speak, that recorded message is saved and transmitted to Gregory, to me? Okay, we can't do that with a Post-it note now. But how do you think we might achieve that today? How could you produce something that you could stick onto a door and leave a message and allow people to tap and leave an audio recording? Could you make something like that today?
Just write it.
Sorry?
Just write it.
You would just write the message, right? So, but the Post-it note has a certain amount of space, and it's on my door or on this wall, and I wouldn't take too kindly to you writing on the wall right there.
Put a QR code?
Sorry?
QR code?
A QR code. What would I do with the QR code?
Everybody with a phone just scans it and then gets to your web page.
So I can scan that, pull up an app on my phone that would allow me to say it, and would send it to somebody, right? How else might you do that?
There's a sensor with some Wi-Fi technology.
Yep, so build some kind of sensor that could detect the kind of tap there, and that could, maybe has a little Arduino on it, and I could speak to that Arduino. How much do you think, though? Yeah?
So, I hit my neighbor's doorbell last week,
Mm-hmm.
and he was not home, but it hooked to him in his office, and he started speaking to me from
Right, through Ring or something, a kind of electronic doorbell.
past the message.
Right, and he installed that on his door.
Right.
Right, so,
He had a hotline to himself.
right, but he doesn't have that. Well, he could install something like that in his office door, and you could perform something like that. But if he wants to put something like that arbitrarily, the thing that's nice about a Post-it note is I can deploy it just about anywhere. And I'm not so worried about that Post-it note after a certain, when I return to that particular space, it wasn't that expensive for me. I can take that and put it in the recycling bin, and it's done. Right, so I want you to think about how we might solve this particular problem with something that is as cheap and as easy to deploy and as simple to work with as a Post-it note, and yet have the computational capabilities. You've proven the point that functionality can be accomplished, but I would challenge you to be able to accomplish it at the cost of a Post-it note. You know how much a Post-it note costs? Rough guess. Yeah, not a lot. So I was in the post office this morning down in Sketty. Sketty Row, is that what it's called? And I looked at, and a post office is not where I would go for the cheapest Post-it notes. But in there was a package of Post-it notes of all different shapes and colors, and 275 of them I could buy for £1.50. So it's less than a penny, right? So could you do those solutions that you talked about and sell them for less than a penny? Probably not. Okay? Let's take another example. You know what that is? Does anyone have anything on their wrist that does something more than tell time? Sorry?
Tells the date.
Tells the date, okay. Anything else? Anything about your own activity? So that is an example of a health activity monitor. That's the Fitbit Flex 2. Costs $100. You charge it, lasts a whole 2 weeks, which is pretty good. And it counts the number of steps and does some other things. And it communicates that information to a nearby device, typically your smartphone. Okay? You familiar with things like this? Does anyone have any of those? Well, you have things like that, right? That rubber bracelet, you know how much that costs? You can go to a website right now. You can order, I think, 500 or 1,000 of them, and they will cost you about 4 cents each. How often do you have to charge that? Never. What if that, at that price, allowed you to count your steps, for example? How would you produce a cheap version of that Fitbit Flex that counts your steps? Any idea? Just go to the store, put down 100 pounds and buy it. Lasts for 2 weeks. Anyone here ever been involved in a study where you get a reasonable number of participants, 1,000, and you want to gather activity information about those 1,000 people? Anyone been involved or heard of any of these kinds of studies? Because there have been some that have recently been published in Nature and in Science. What you can say when you start to look at very large numbers of people. I have a lot of colleagues that do these kinds of studies, and they can't afford to give 1,000 people a $100 device. But even if that device was $1, if it lasts for 2 weeks, they can't rely on the participant charging the device, even if it's every 2 weeks. So you'll get 2 weeks worth of data, but if you want a year's worth of data, you rely a lot on the cooperation of the participants. What if the participant is a sheep or cattle? There actually have been studies where they have created devices that are solar powered or harvest energy in a variety of ways, and they put them on animals in the wild to kind of track their behavior. So they've been pushed because they recognize that, well, I can't control how this animal, this participant, is going to use this particular technology, so I really have to make it durable. It can't change the batteries because I want to track their behavior over years, and it needs to give me some relevant information. So these are interesting kinds of goals for how can you produce computational devices that are, effectively disposable, cheap, but provide computational capabilities, or enduring, last for a long time, and give you information that would be interesting about human activity. So these are some of the things that motivate what I would like to be able to do. So, one question you might have, that's interesting, Gregory, but why do I care about having a health activity monitor that counts my steps? Or why would I want a Post-it note on my door that records a message of someone going by? Aren't those first world problems? I think you're right. Ask this question. What happens if I put that Post-it note on my door and it falls down, someone walks by, it goes on their shoe, and they walk away? What happens to me? I'm at a university that likes to think that it's prestigious, but more so likes to think that there are really talented people all around, and they reach out to you occasionally. So what if someone really interesting and important comes to my office, I'm not there, and then walks away? So I lose this opportunity to find a potential collaborator. I also lose the opportunity to have a student come and complain to me about a grade they got in a class. So, but you would argue, no big deal. You lost that piece of paper, fine. You get back to your office. If they really want to get in touch with you, they'll find a way of doing it. Not a really big problem. So, here's an image, and I just got this morning from Harold Thimbleby. I want to put the acknowledgement in here. It's hard to make out because of the contrast here, but that is an infant child in intensive care. What's hard for you to make out is that this is a whole stack of medical equipment that's attached to this little infant. And the important thing here is that almost every one of these devices has a Post-it note on it, written by someone saying something about the importance of that. What happens if the Post-it note falls off of that? The baby could die, because it might be very important information about dosage or about what has to happen next. And if that Post-it note falls off, the reminder to the person who wrote it or the next staff that come in don't see it. And yet, this is in the US, arguably one of the better critical care countries in the world, and they're relying on this technology, which is useful, very easy to use, very flexible, but if it falls off, that poor child's life is in danger. You said, okay, that's a relevant problem in a first world. Here is, and I'm sorry again for the contrast, this is a corridor in a Mexico City hospital. Bunch of patients sitting along the wall. Each one of them has an IV attached to them, and each one of these IVs has a Post-it note attached to it of relevant information for that particular individual. So this is not something that just is a problem or an issue in a first world. Because you might argue, over here, how would you do something better than these Post-it notes? You're technologists, how would you do better? Any idea how you might get around the problem that this Post-it note has information that if it falls off, we lose it? How would Elon Musk solve this problem in his Teslas? A huge display. That's the solution. Rich country, expensive displays we put. The problem with these devices, they just need to have better color monitors, and you could even speak the information in there. That's the solution that you might do. Right? And that might work in certain countries, but that's not going to work everywhere else in the world. So we have to think about solutions that are meaningful, and I would argue practical to be deployed in a variety of different situations. So that's my motivation. I think we've got this big gap between Weiser's vision of ubiquitous computing and what we have today. And there are different ways we can think about solving that. So what I'm going to talk to you about is computational material. It's a new technology idea. And I'm going to contrast this with what I think is what we have with the Internet of Things today. The Internet of Things is not really an Internet of things. It's an Internet of devices. You know, other kind of computational objects that we add some capability so they can communicate with each other. And that's nice. And there are, estimates say anywhere from 20 to 30 billion connected Internet of Things devices by the year 2022. Okay, that's a lot. But what about something like this, where all of the surfaces in your environment have this ability to sense, communicate, provide some sort of output, compute, store information? That's what I call the Internet of Materials. And the question is this just give it time and the Internet of Things will become this Internet of Materials? Or do we have to think very differently about how to get to there if we want to get there? So I hope by now I've convinced you that I think there are reasons why we would want to get to here. That corridor in Mexico City using the Post-it notes. And I also want to convince you that we're not going to get there using the same ways we think about what a computer is and how we build those computers today. That's what I next have to try to convince you of. So there are three things, I think, that prevent us from getting there. Power. If you have mobile devices, probably the single most important consideration when you're designing it is, how am I going to power it? And how big does the area in this device have to be to host the battery? And what will its usage pattern be? And how will it be recharged if it ever needs to be recharged? Or how can it be plugged in and stay plugged in? That's the biggest challenge of any kind of mobile technology. How is that Post-it note going to harvest the power it needs, or have the power it needs to last as long as it needs to last? Some Post-it notes you might have for, a minute. Others you might put in place, and as long as they stay stuck to where they are, you'll want them to last forever or a long time. So cost. Even though you might think that computers are a lot cheaper, or the components of computers are a lot cheaper today than they were in the 60s and the 70s, they are. They're not nearly cheap enough to do the kinds of things that we're talking about here in terms of producing a Post-it note, a pack of 100 Post-it notes that would cost about a penny each. So there's both the cost of the materials and the manufacturing processes that would allow you to make them at large scale. And the last thing is that today, things that are connected to the internet, they look like computational objects, right? The object most of you have in your pocket or on your wrist or in your backpacks, you can identify them. Even, a refrigerator that has a display that's connected, you can tell that it's a computer. It doesn't look like the furniture that we're sitting on, or the floor, or the clothes that we're wearing. or a Post-it note or a rubber bracelet. So what we're going to try to do is develop solutions that follow these kind of guidelines. These will drive whether our solutions are any good. You never have to change a battery. They're cheap enough to produce at large scale. And they either themselves look like everyday materials, or if they're put onto some other object, they don't change the character of that object they're placed on. Okay? So I'm going to give you a few examples of getting toward that vision. I'm going to show you 3 or 4, depending on the time we have here. The first one I'm going to start with, and I have a few props to hand off here to give you some idea. This first one I'm going to look at is the ability to take a thin, flexible, multi-layer material. So passing out something that's thin and flexible. These are 2 of the 4 layers. This is paper with copper on the back of it. And what do you notice about that piece of paper?
Very thin.
Very thin. Anything else you see?
It's transparent.
Is it transparent? Why do you think it's transparent?
It has a hole.
Yes, it has a pattern of holes cut throughout it. So how many here have ever taken a balloon and rubbed it across some carpet? What happens? Yeah, it builds up some static electricity, and you could, hang it to a wall, or you could put it near someone with long hair, not me, and their hair would come out. You know what that's called? He keeps raising his hand to move the camera, but you're not raising your hand to volunteer. Next time, I'm going to make you volunteer and answer. Do you know what that's called? Are you familiar with that? You combed your hair in dry weather, and if you have long hair, the hair follows the comb, depending on what the material of the comb is. So any 2 materials exhibit this phenomenon, that when they come in contact with each other, there's a redistribution of charge at the surface of the 2 materials. One of them will redistribute such that a positive charge accumulates. The other will get a negative charge, and it's a relative property. Some of these materials, that property is very pronounced. So if you take 2 materials like copper and plastic, and you put them next to each other, I'll start this somewhere else. So this is an example of that paper, and on the other side is a piece of plastic that's got copper on the side of it. So we've got a 4-layer material. If you bring the copper and the plastic next to each other, they experience a very strong triboelectric effect, it's called. Strong distribution of charge. When you separate them, you got positive and negative, you build up an electric potential. What happens when you have an electric potential if you provide a way for the current to flow? It'll balance itself. So I build up an electric potential. I have copper on this one, and I put copper on the other side of the plastic. I connect those. Then when they separate, the current's going to balance itself. So as long as I have contact and separation and repeat that, I'm going to produce an alternating current. The interesting thing about that is that alternating current, if you measure its voltage, it's going to be reflect the power of the source that caused the contact and separation. Now, I'm going to play this little video here that's going to describe this in a little more detail.
We present Saturn, a flexible thin material that can easily be embedded on everyday objects to enable them with self-powered sound sensing and sound energy harvesting capabilities. Saturn consists of materials which are thin, flexible, and cheap. Paper.
So that's the paper?
Called PTFE.
Yeah. And a plastic.
It's a series of holes laser cut in a specific pattern. Both layers, PTFE and paper, are coated with a thin conductive layer of copper and joined together using glue dots in a grid-like pattern. When sound reaches Saturn embedded into an object or surface, its structure microvibrates, resulting in both layers getting in contact, generating negative charges on PTFE and positive charges on the copper-coated paper.
The one thing I'll add to that is when you have all those fine dot patterns, you're producing a wide variety of different kinds of vibrations between the 2 layers. The copper on the side of the paper and the plastic that has copper on the other side of it. So you're getting a lot more vibration. You've designed something to increase the likelihood of that contact and separation.
As the layers separate, potential differences build over the two copper layers, causing the current to flow towards PTFE.
Paper, copper, plastic, copper.
And the layers getting closer and in contact again, resulting
So.
in the reverse direction of current flow that completes the cycle of electricity generation.
Okay? So just to give you an example of what it sounds like when we take that sensor and pull off from the electrodes the alternating signal.
This is audio recorded from Saturn.
Right? So that one that's going around, there are two that are going around. The one there is more than just Saturn. Where's the other one? One's got a little, yeah, that one. That's the quality of sound you'd get from that. If you just took those endpoints that your fingers are on, that are on the styrofoam, and just connected those into an oscilloscope or into a computer and took the signal, that's what you get. Okay? Pretty interesting. But that's only a sensor. You got to connect that to something to essentially extract the signal and do something with it, play it back. So the next part, and that's the one that's going around that has the, not that version of it, but there's another one that you just had, that one there, that he's holding right there. That plate that's printed next to it, that's an antenna. That's a printed antenna, and between the sensor and the antenna, there's a single transistor, a JFET. And there's this very interesting phenomenon. Well, there's an everyday kind of phenomenon. You know when you've got the sun and you have a mirror, and I want to communicate to you, I can kind of angle that mirror, and I can blink light to you to send a message. You can do something like that without light being the source, but with a radio frequency wave, RF, being the signal that's being reflected off something and communicating information. So when an RF field is incident upon the antenna connected to that sensor, the sensor coupled with the transistor affect the reflected information. And that reflected information carries the audio. So now you have something that's a passive wireless communicator that's also a microphone. I'm not going to show this video. Yes, I will. I'll just show one piece of it.
Hello, hello. Audio from Booth. Audio from Booth.
No fixing of that signal. So, and all that's happening here is we've got two antennas. One's a transmitter, one's a receiver, sending a 915 megahertz signal. It's bouncing off the Saturn patch with antenna sitting right there. Nivedita, the student, is speaking to the patch. Okay. So that becomes interesting because now you have not only a sensor, but a sensor that can wirelessly transmit its information somewhere else. So there are two ways you can do this. One involves using a computational device like a transistor, but in fact, you could directly connect the sensor, that patch that's going around, to the antenna, and you'll get a different phenomenon, but it'll essentially produce the same kind of analog backscattering, so a passive wireless communication. So I now have a thin and flexible material that in the presence of an RF field can wirelessly transmit what it senses. So that's the first example of a computational material. I won't spend as much time on these other examples, but just to give you a flavor that this can be done in a variety of ways. So here's an example of a stretchable cord that's going to use the exact same phenomenon of this triboelectric with electrostatic induction or triboelectric nano generator. And what it's going to do, it's made of different materials. So this is a series of silicone rubber rods that are laid on top of each other with some conductive threads of different materials in between. And what happens when you do that?
We introduce certainty, a self-powered sophisticated deformable cord sensor. Using principles of turboelectric nanogenerators, Serpentine senses mechanical deformations without an external power source. Serpentine can detect 6 unique field interactions: buck, twirl, stretch, pinch, wiggle, and twist.
Unfortunately, I can't turn the audio off here. How do I turn this sound off? I can just recite you because that was That was recorded using the earlier version of Zeus with the quality of audio, sorry. So what's going on here is you've got a cord, and when you manipulate it, the energy signal you get is characteristic of the way it was manipulated, whether it was stretched, whether it was twirled around your finger, whether it was pinched. So that's what this is just showing, that you get a different signal when you do different things to the cord. And then some suggestions of how this might be used. So it's a cord in a hoodie, and you can pull it, recognize that pull, and it does something. It controls the sound, or that's a game player. The harder you pull back, you can actually not just measure or detect what kind of action you do, but the intensity with which you do it. So you could turn it into something like a game control that looks more like something in the physical world. So the only reason I show you that is to say we can do the same thing that we did with that audio sensor, the Saturn patch, but in a different form factor, creating something that's kind of fun, graspable object. Last thing I'm going to talk to you about is what if I can make a surface that would be aware of things that are going on near it. So in this one, we're going to use a different kind of technology. So these are with some photo-organic printed electronics experts. What does that mean? That means they can print sensors that are thin and flexible, and we can print them on a flexible circuit board. And effectively, I have here a 4x4 array that can detect motion above it, so I can do particular gestures I want. It can detect direct touching, so multi-touch sensing, and then I'll show you some other things that this can do. Now, these are really cheap materials, so it doesn't really cost me much if I don't get them back, but it makes the talk that I have the rest of this week very difficult to do. So if I could have those materials back, I'd appreciate that. I'm not going to show you the video for this. If you want, I can show you afterwards. What I'm going to talk to you about is something you could do with this. The video there shows hover actions, shows, multi-touch gestures. And the point about this is that it's extremely low power. So that is not self-harvesting in the sense that the examples I showed you before, but it runs at such a low power budget that any kind of conventional strip of solar collecting material, I can attach to that, and that provides plenty of enough power for this thing to work. So you can effectively get strips of this solar material and put it around the perimeter of that. And that would power the ability to not only detect the sensing, but also transmit it using conventional Bluetooth technology. That's what we've been able to show. But here's some other examples that you might do. So I talked about that health activity monitor. Let me give you a way that those are typically done with what's called an inertial measurement unit. An accelerometer is one example of that, a 3-axis accelerometer that just measures your kind of movement. Well, if I've got a band around my wrist, and I have a series of photodiodes along that band, and on the left here is a prototype we've done without using the thin, flexible versions of the photodiodes. Along here are just conventional silicon photodiodes, so they're not flexible, but you can line them up along this particular band, and then I can put it on my wrist. Now, what happens when I walk? What happens when I walk?
Your wrist is moving?
Yeah, my arm is moving, right? And my body is going to block ambient light from getting to different parts of that of the diodes on here. So in fact, what's showing up here on the right, and this is just a static view, but this is essentially a visual display of the incident light on the 8 different photodiodes around my wrist. And if I played this over time, you'd see that as I move, they change, and I can detect when I'm going this way, when I'm going that way, and that way is half a step, or depending what you consider a step, you can count the steps with something. And again, this doesn't require a battery to do it because you can use ambient light to power the ability to not just for the photodiodes to work, but for them to communicate that information to something else. Okay. But it's even more interesting than that, because the difference between these printable photoorganic photodiodes and a regular silicon photodiode is that the printed ones can take on a variety of different shapes. So I talked about being able to detect this motion by using a series of 8 photodiodes. And the reason there's the 8 is so that it goes all the way around, and I don't really care how this thing is oriented on my wrist. It'll work however you put that band on. But now I could actually print the photodiode with a particular shape, and what results is a series of voltage measurements over time. So if I print something that's that size and it passes this way, you get a different voltage reading than if you change light as you pass that way. So the shape of the photodiode would allow me to print only one photodiode and still get the same kind of information of walking. And these photoorganic electronics are very cheap and simple to manufacture compared to a silicon photodiode. Okay, so I've got 7 minutes to the hour. When do you want to stop? If you want to stop now, you just get up and leave. That's totally fine. I have a number of different research opportunities to explore here, or I can just end with my concluding thoughts, and we can have a discussion if you'd like. So let me just show you 4 different research areas that I think can be inspired by people who want to look at this world of computational materials. How you make things power savvy, how you change production practices, produce computers in ways different than the way we produce computers today. How do you find why the user experiences, the applications or uses of these computational materials, and other principles that drive this kind of innovation? How do you think about privacy, sustainability, and other things when you build a world of these computational materials? You can hear me talk about one of these. Which would you like me to talk about? Okay, I was going to say, I'm going to modify that. You have to hear me talk about one. No, you don't have to. You can just get up and leave. You want to hear about the first one? Yeah? Because who cares about privacy, right? Power-savvy platforms. So, the thing I showed you with that audio sensing patch that we called Saturn, or the cord, those were examples of the phenomenon you're trying to sense produces the energy in order to sense it. So my voice provided the energy to record for Saturn to sense that audio. The manipulation of the cord provided the energy to detect which manipulation I'm doing. That's a really wonderful situation if you can get it. Right? So a self-sustainable sensing capability. It's a powerful general idea. What are other things you might do that are phenomena you want to sense that you can harvest energy from? Any ideas? Opening a door. That's a really interesting example because the photodiode I showed you, if I place that on the edge of a door, when I open, it's exposed to light, so it'll change. But how do I get the opening to produce the energy to do that?
You've got movement across the surface.
Mm-hmm.
You've got the opportunity to generate power the same way.
Right, so if like the wind going across it as I open the door is enough vibration, I might use the TENG effect to do that. What we've done in practice with that 1-bit photodiode is we just wrap around the edge of the door some solar collecting photovoltaics, and that generates enough energy so that when you open, you can detect the opening and closing. But that's a good idea. I mean, the fact that I open a door, the hinge back there might be where I could get the sliding that would provide the information that I want. Okay, any other examples of a phenomenon you want to sense that generates the power to sense it?
Walking.
Sorry?
Walking.
Walking. So the TENG material that I showed with that the serpentine cord, imagine layers of that in your insole. So as I'm walking, I'm producing the squishing that will generate. There's also people that looked at piezoelectrics in the shoe to essentially generate enough energy to do what? To measure my steps. Right? The disadvantage there is that every kind of shoe wear I have has to have this capability in order for me to count my steps. Okay? Let me give you another example that we're working on. Water. How could the presence of water produce the energy to detect water itself? Anyone here flown in the last 25 years? Right? Anyone here paid attention to the safety video on the plane in the last 25 years? Right, once. Do you remember the life jacket that you'd put on if you're going over water? And on your shoulder, there's a little light that will come on that's activated by, and how does that work? Water, with the right chemicals, can act as the electrolyte in a battery. So as long as you can get the water to go between the cathode and the anode of a battery, you can produce a significant amount of energy to power a light for an hour or two. How could you produce a thin, flexible, easily manufactured material that might be deployed when they do building in the US? I think it's true here as well. There's a layer that's put in of looks like plastic-like material. One of the brand names is called Tyvek in the US, made by DuPont. It's a wind and water barrier. But what if that wind and water barrier material could also tell you where water is encroaching and communicate that out? So we've developed an example of a multi-layer material that water can penetrate and produce enough energy to power a variety of different wireless communication capabilities. So water senses it. But you can think of other chemicals where you might want to do that as well. Carbon monoxide, for safety purposes. Ammonia, which is often provided by, given off by food as it's spoiling. So you can think of different scenarios like that. So that's self-sustaining solutions. You can either have the sense phenomenon produce it, or you can leverage an ambient signal source. So where's that OptoSense, the one that's the, not that, that's Saturn, right? That's the audio sensor, the other one. I want that too, so yeah, that one. So how would I get the information from there to somewhere else? So I'm touching this, and I want something else to know that I'm touching it. What did we do with the audio? Here, we used backscatter of a radio signal. But the problem with this backscatter is I had to use a separate 900 megahertz antenna to transmit the RF and another one to receive it. Not very practical. What kind of ambient RF signals are in our everyday environment? Sorry?
Phone signal?
Phone signal, so cellular, the 2.4 gigahertz. 2.4, 5.8, the wireless infrastructure. And those are nice because they use a small antenna to connect to. But there's also a lot of FM transmissions in our environment. And FM has some good things and bad things to it. The bad thing is you need a pretty big antenna to receive FM. You can do some things to make that smaller and still get a good enough signal. And most phones, well, the Apple phones up until 1 or 2 generations ago, every Android phone has an FM receiver. So what if I can use the ambient FM signal in my environment to reflect, 2 meters? As far as I can get my hand away from where my phone is. If I can reflect 2 meters, I can get anything I touch on any surface to communicate back to my phone without this needing a power source. So you got to think about those ways of practical ways of getting using the ambient environment around. Think about a car, an automobile. Where can you sense, where can you harvest energy on an automobile close to where you might want some sensing to happen? Near the engine? Why? What are you going to harvest from? What is the energy you're going to harvest? The vibration. Right, so near the engine or on the, it's not called the hood, bonnet, right? The bonnet of the engine, okay? You can also harvest from heat gradient. So where's it hot in your car? The engine. Where else is it hot in your car? The brakes. Where else is it hot in your car? Sorry? Carburetor. The seat, if you're sitting on it, maybe. I would question whether that's true in December. How about the exhaust pipe in the rear of the car? So the thing about this is to think not only where can you harvest energy, but where can you harvest energy where it makes sense to do sensing and computation. So the exhaust pipe is facing backwards. So it would be really good to power something that is sensing behind you, like a backup detector. So if your car doesn't have a backup detector, could you retrofit it with something that harvests energy from the exhaust pipe and does the range finding to be able to determine how far away something is, or even transmit an image from the rear of the car to the driver of the car? So thinking about those opportunities, the windshield, the windscreen, very good for collecting solar energy, actually not very good for doing temperature differential, but good for solar energy collecting. So just thinking about the different ways we can harvest energy in places where we can use it for computational sensing purposes. And the last point I'll have here, and then I'll stop with this and give you my final concluding thoughts, is when you're designing something computational, you don't always need things to be done in the digital domain. Sometimes doing things in the analog domain, like that backscatter I talked about, that's an analog backscatter. It's a physical signal that's being reflected. There are advantages and disadvantages to the analog-digital trade-off, and really understanding those as someone who's architecting a device really opens up opportunities to do things you want with a power budget and form factor that you'd like. Okay, so I will skip out of, I'll just remind you again what those challenges are, but I want to end here with a concluding thought. There are lots of amazing insights that I'm skipping over here, just so you know. About thinking differently. So, you're familiar with Moore's Law. Do you know what Moore's Law actually said? Do you know what Moore's Law actually said in the late 60s? See if I can show you the actual wording of Moore's Law, because this is interesting. The number of transistors you can buy with $1 will double every 1 to 2 years. This is a result of increasingly clever ways to manufacture integrated, so integrated manufacturing circuits at a lower cost with more and more components. That's what Moore's Law was, or is. I can show you the success and the lack of success of that. But the way we colloquially think about Moore's Law, and what I'll call Moore's Law thinking, is that computers are always going to get smaller, faster, and cheaper. Right? So I've got this phone here. You know, this same phone in 18 months will be either it will be cheaper and do the same thing, or for the same price, it'll do twice as much as it does today. Right? Do you believe that anymore? If you do, you shouldn't, because it is no longer true. People will argue back and forth about whether Moore's Law is over. My argument here is whether or not it's over, it's a particular way we think about being creative with computing. And here's what it influences. So we can take a variety of different domains. This is portable computing, and that is a portable computer in 1986. Why do I know that? Because that's the portable computer I brought with me to Oxford. It looked like a luggable sewing machine, right? 30 years later, I can buy something like this, a laptop that's a lot smaller. It costs way less than my compact portable cost, does way more. And that's the kind of thing, and the result of Moore's Law, right? Because every 18 months, it became cheaper and cheaper to give you the same level of functionality. We see this in mobile communication. That's a mobile phone circa late 80s. This is a little deceiving because this isn't a single mobile phone. This is a Motorola mobile phone here that has a variety of different attachments you can put on it, right? 30 years later. That does way more than this does. It's something that's easy to carry in my pocket, and, you know, thank you, Moore's Law. We think of other domains. Augmented reality. This is a really bad picture of an augmented reality demonstration in the late 90s. Someone's wearing a backpack. They've got a big antenna coming up. That's a GPS receiver. Lots of batteries on them, and it will produce very crude graphics of the name of a building as you walk around outside. And less than 30 years later, here's a version. This is Pokemon Go. Oops, sorry. This is Pokemon Go that works on a mobile phone that does augmented reality in your hand. Same thing happens with virtual reality. What was a big clunky prototype becomes a sleek and sexy looking solution 20, 30 years later. And why do I point these out? Because we assume that this is going to happen. And so what we do as researchers is we build the clunky prototype that doesn't run in real time, needs a lot of batteries, is very heavy, and we don't worry about solving all of the user experience problems, because the things having to do with size and running in real time, those, you know, they say give it 18 months. Moore's Law will solve that. Okay, well, I don't think that's the only way we can think, and maybe the case that we can't think about that anymore. So that's Moore's Law thinking. When you think that computers will always get smaller, cheaper, and more powerful, you think about building clunky examples of what the future might be like, and then you step away and just let the future take it. And it'll create your vision in a better form factor. So the law I want you to be influenced now is to think differently about what a computer is, thinking about these computational materials, but think in the mindset that these things I showed you here, these are really crufty looking, right? But they're going to get nicer looking, they're going to get cheaper, they're going to get more functional, and I'm going to be able to manufacture them at much larger rate so that you can have lots of these for a little bit of money. And I've shown you a few examples of where we might do that. Right, that little optical wristband, I can turn that into something that passively communicates to my smartphone and do activity recognition. I hope I've shown you a glimpse of being able to take something like this, which doesn't quite look like a Post-it note, but it's much closer to a Post-it note than some of the suggestions you might have offered at the beginning about how we might create that thing I can tap on my wall and record. You know, it might not take that long for us to be able to turn this into something that's as cheap and looks much like a piece of paper, like a Post-it note. And then ultimately being able to produce water detecting material that would cover an entire building at the cost of the existing materials that we use today. And to get there, we not only need to worry about those 4 research problems, but we got to worry about who we let influence our thinking. So on the left here are people I work with at Georgia Tech and the University of Michigan, but what's more important is the list of disciplines that they represent. And what's even more important is students or anyone thinking about being influenced by this, you need to let yourself be influenced by all these different kinds of disciplines if you buy into this idea that there's a different way of thinking about a computer. I think there are commercial opportunities here because I believe this is an alternate computing industry. How is it going to emerge? Who will make it emerge? These are all the students who've really done the work. I've shown the faces of the faculty and the names of all the students. And with that, I'll thank you for your attention, and I'm happy to take on any questions. Thanks.